Scientists observing owl and hawk populations collect the following data. Their initial count for the owl population is 245 owls, and the population grows by 3% per year. They initially observed 63 hawks, and this population doubles every 10 years. So you want to find formulas for the size of the population of the owls and of the hawks as functions of time. So you'll find one formula for the owl, should be the easier one of the two. And then you're going to work on a formula for the population of the hawks. All right, so I would like you to, I have confidence that you can give this a good try and see if you can get both those formulas. So go ahead, pause the video, see how you do with those, then we'll come back and work them together. All right, so for the owls, it says our starting population is 245 owls, and it grows by 3% per year. So that means my R is 0.03, and if I add 1 to that to get B, I get 1.03 raised to the T. Right? And then for the hawks, so it says there's initially 63 hawks, and that the population doubles every 10 years. So if it doubles from 63, that means I'd have 126 hawks, and that'll be equal to 63 times b to the 10th. And that 10 is because it takes 10 years for them to double. So if I divide the 63 over, I get 2 is b to the 10th. So b is going to be 2 to the 1/10th power, which is approximately 1.0718. So that means the population for the hawks formula is going to be 63, which is our starting population, times 1.0718 to the T. All right, so part B, when will these two populations be equal? So whenever we're looking for equal, we're looking for where they intersect. And that means that we want to set these two equations equal to each other. So we're looking to take the owls and set that equal to the hawks. So it gives me 245 times 1.03 to the T is equal to 63 times 1.0718 to the T. All right, at this point, there's a couple different ways you can use logs to solve this. I'll show you one way, but if you have another way that is mathematically valid using logs, that's totally fine. So I'm going to stick with our principle of getting all of the pieces with t to one side and everything without t to the other side. So I'm going to divide by 63. So I'll get a 245 over 63. And then I'm going to divide both sides by this 1.03 to the t. So what that does is it gives me 245 over 63 is equal to 1.0718 to the t over 1.03 to the t. Okay, and since both of these have the same exponent, what I can do is I can put those bases in parentheses, still being divided, and move that to the t outside here. So it's just using some properties of exponents. And now that I have a piece of t isolated, I'll apply a log to both sides. So you can use the common log, you can use the natural log. Either one will work. You just need to make sure you apply the same one to both sides. And when I apply that natural log, that t can come down in front. Okay. So that's why we use that, the log. So that allows us to bring a t out of the exponent down in front. And then to solve for t, I just need to divide this over to this side. It's quite a mouthful to say, but t is going to be the ln of 245 divided by 63. All of that over the ln of 1.0718 divided by 1.03. Okay, let's look at how we're going to get that in our calculator. So I have ln of 245 divided by 63. And I'm going to divide it by ln of 1.0718 divided by 1.03. And that gives me about 34.1 years. So after about 34 years, those two, the owl and the hawk population, will be pretty close to equal.